welcome to this week's episode of Automate It. Automate It is our weekly podcast where we talk about robots, how much we love them, and how much they hurt us so incredibly deeply. I, of course, am Stefan and CEO and co-founder here at Polymath Robotics. And sitting across from me is someone, and their shirt says, "Hello and welcome to this week's episode of Automate It." Sitting across from me is someone whose shirt says, "Hello and welcome. Welcome to this week of Automate It."
Sorry, listeners, I'll go press the reboot button.
I'm just in a recursive loop. So this is Automate It. We have two sections of this podcast. The first 15 minutes or so, we'll play a game where we spitball a robot into existence. And the second 15 minutes, we'll talk about some sort of topic in robotics. Ilia, what are we going to talk about this week?
Hey, we're going to talk about how simulation is useful or not useful to robotics and where to use it. Mm-hmm. And then we'll lead that into what sort of sensors in particular are good to simulate.
Yep.
And radar and how that impacts
radar. We're
Yep.
primarily talking about the character from MASH, but then also sometimes the sensor itself that there's probably been more radar sold in the last 10 years than I think you could make a bet that there's been more radar sold in the last 10 years than since World War II.
Yeah, I'd take that bet.
Yeah.
But that's true. Microcontrollers too.
Yeah, but I'm including all fighter jet radar and boat radar. And
I think fighter jet radar makes up the vast minority of total radar ever.
That's what you say.
Maybe up to World War II it was the majority, and then post that,
I don't think there weren't too many fighter jets with radar on them in World War II.
Or planes in general.
I think there's just the 7 jets that, only 3 of them flew more than once.
Yeah.
But with that being said, let's play a game. So this is our game where I'm going to draw a technology card to kind of simulate what technology we have to use for the robot startup we're going to build. And Ilia's going to draw a business card. Ilia, what's your business card?
All right, let's look at this business card. We haven't done bar in a while. Let's do bar.
I think one of my favorite spitball robots is the bar robot we did on episode some number that could be inserted later, where it was just a series of electrified train tracks that brought beers exactly.
That's one of my favorite ones too.
I think that's pretty great.
It's a competition in that and Sewerbot.
Yeah, Sewerbot was good. I mean, radar
in a bar
happens to be
what
I drew. Actually, not that I've ever faked any of these card draws before, but this one is actually legit. So what are we doing with radar in a bar?
Yeah, good question.
So my wife used to work for a company that several pivots earlier was using radar in senior living facilities. Basically, the CEO's grandma died, and part of why she died, she got some sort of infection, fungal infection, something. She had a big tapestry on her wall. And in some weird corner of the back of the tapestry, some mold or something started growing, and that set her on the illness that led to her death. So what this company was originally doing was trying to put a radar in each room in a senior living facility so that in a very non-invasive way, they could see if you were moving regularly. Yeah. Because the people there could have known, weeks earlier that she wasn't doing well had they just noticed that she was no longer walking around her room all that much. So you could use radar to kind of constantly measure how many people are in your bar. And then... Well, wait, here we are.
All right.
How many people are in the bar and then do predictions on when the bathroom needs to be used or when the bathroom should be cleaned.
I have a better one. Okay. I skimmed a paper a long time ago where it was actually a study to find head injuries for football players. So what they would do is they would scan the walking pattern of a football player and try to figure out if they've been traumatized.
Yep.
And
just childhood or
specifically in the last 5 minutes of play.
Yep.
Great sport.
Your son's going to play it, right?
No, absolutely not. Absolutely not. And what they actually found is to simulate this, they put on these lenses they called beer goggles, which would make you look as if you were severely inebriated. Mm-hmm. And then they found that they could actually measure inebriation based on walking pattern, which makes intuitive sense, but a lot more subtly than you'd think using radar.
Huh.
So specifically, we can figure out how inebriated somebody is if we can measure their walking pattern.
Well, so I don't think a bar, though, actually wants to know if someone's all that inebriated. Like, theoretically.
I think the law says otherwise.
Yes, I know. That's why they don't want a sensor that tells them.
Yeah.
I think most bars operate in a gray zone of, oh, I don't know how they got so drunk. I served them 48 Long Island iced teas in the last 2 hours. I assumed they were going to friends or they were pouring them out empty. I don't think the bars want this information. However,
I think a Long Island iced tea by itself is a red flag of just like for sure underage drinker by default. Nobody else orders that.
As a story to the listeners that everyone here has heard more than once, I was once at a establishment in San Francisco after legal closing hours at 4 or 5 a.m., ordered a Long Island iced tea, and then was carded. When I asked the bartender, hey, you've been serving me for hours, why are you carding me now? She responded, I've literally never seen someone over 21 order this. So take your Long Island to get the out of my bar.
That's right.
So that's a good point. I think we just do it as a public health thing. It's radars in, I think you could say bars are high risk areas for people who probably have underlying conditions. And if you put radars in bars.
Such as alcoholism?
Yeah, or trauma. Like
trauma leading to alcoholism?
And from.
Okay.
And if you just put radars in public establishments, you could find out people who might have underlying neurological conditions. And then you could do that across the master health database that totally exists of all people.
Right.
And then connect that to the microchip in their arm.
The government's not going to be upset at you for HIPAA violations or anything.
or the fact that there is no master system.
Yeah.
But yeah, theoretically, you could like basically use it as a measure of public health.
I wonder, because there's always problems with people being inebriated and then operating heavy machinery in construction or mining or whatever. Like, what if that is just everybody has to go through the security gate to get onto the work site? There's a sensor there. It'll catch you just by walking in.
That's not in a bar.
Well, they're taking the bar with them to the work site if they're that inebriated that it's caught.
That's interesting. I mean, you could basically, I think we're dangerously getting close to a real business where you could put in dangerous work sites, probably not construction sites, but more like factories.
Or mines.
You could put a bunch of, mines, like it'd be hard to, you'd have to constantly move these radars. But like in a factory, in a car factory, you could put a radar on the ceiling every 300 feet. And basically say which workers are potentially unable to be doing their jobs safely.
So I think this kind of comes down to a deep tech dive into what radar is and what the modern radar is versus World War II radar.
Yeah, we can save that for the later half. But let's get back to bars and radars. Well,
I was going to say the reason I was going to dive into it is radar's actual discrimination between multiple moving objects is not actually that great. It's not fantastic. It's recently become more reasonable and we use it as a safety sensor but it's not fantastic. If you have a group of 50 people, you're in a world of pain. If you have a group of 5 people, sure, it'll work fine.
Yeah. So in my favorite bar in the world, where they sometimes fit 70 people into approximately 150 square feet, radar would probably not be useful.
You'd get pretty garbage.
Whereas at like a TGI Fridays, you might be okay.
Oh boy.
7 square blocks with 14 people at the bar.
Yeah, exactly.
Well, and I guess also the another challenge with radar is matching radar returns up with an actual individual person. You'd have to tie it to cameras to say this blob that walks funky looks like this with a camera. You can calibrate those 2 sensors, but you need an additional sensor to get it to be something valuable for the purpose of who's walking around with undiagnosed brain trauma. I
mean, I think if we're going to go full on dystopian when we're monitoring our bar patrons, you put a small, because it's robotics, right?
Yeah.
You put a small little hand tilt or robot arm on the ceiling with a floodlight, like a bright red floodlight. And when it detects this walking funny pattern, it just points the floodlight at this person and just this person, bad.
This person has had some sort of trauma.
Yeah. It's the trauma light. That'll go over great.
We don't have to worry about HIPAA violations because we will have never been compliant.
Well, no, not even. Well, actually, it's an interesting gray area because we have no actual idea who this person is.
Yeah.
We're just saying This blob is suspicious. I don't know who it is. Could be you, could be me, could be anybody. But this blob is suspicious.
Next, we'll just have a roving radiology machine, X-ray machine, and just say, oh, this person has 5 tumors. That person has 10 tumors. 20 tumors over there. Don't know who any of these people are.
Exactly.
But we're announcing it loudly as you walk through the bar door.
Yeah. Yeah. What you do with that information is your problem. There's going to be an insurance agent posted at every bar in the U.S.
I mean, we could just ping them automatically.
Yeah. Well, there we're crossing a line, I bet.
All right. So in the bar, we can measure how drunk people are. We can measure if people have underlying health concerns and get it back to mass data. You could also use it as a measure. You could use it as a measurement of how many people are in the bar.
Roughly.
Yeah. And then more or less be able to say, oh, you need to bring more of your back of house people to the bar to help serve drinks because there's an onslaught right now.
Well, yeah. I mean, it's much better to have a very technically sophisticated solution than to just look around the corner of the restaurant.
Well, that sounds impossible. And restaurants famously have lots of money for expensive hardware solutions. Yeah. It's an easy market to sell these solutions to.
Yeah.
But the problem is, I think if it's just a mounted sensor, I don't think it's a robot.
Yeah, that's why the arm with the bright red floodlight.
Yeah, but you could have a floodlight without an arm.
Well, pan tilt unit.
Yeah, I think maybe we need arms to scoop up the people who have underlying trauma and present them to the ambulance.
Well, so here's the real thing. From a distance, you're not going to be able to diagnose very accurately. So what it is it's ceiling mounted strong arms that first, the bright red light points out the person. And if you're in a crowd and somebody beside you gets lit up, the first thing you're going to do is step back because you're going to be like, what the heck is going on? Yeah. The second thing that happens is giant robot arms swoop down from the ceiling and pick up the person and say, you may be in danger.
Yeah.
Moving you for additional processing.
Then some additional instruments come down from the ceiling and probe them.
Yeah. Great. We're going to have a very popular bar.
If we want this to move around more easily, we can just put it in a flying saucer. It'd be far.
There you go.
You can go from bar to bar.
Well, that solves the drunk driving problem. It's just random sweeps, only in dark roads in the middle of nowhere, Kansas. This flying saucer comes down and makes sure you're
only
not driving
with people
drunk.
who are credible enough to get a little bit of play, but not a significant amount of attention.
That's right.
Yep.
That's right. U.S. government confirmed UFOs are real. They're out there, folks. Purely a joke, to be clear. Do not email me.
Yeah, I think we are oscillating between things that look like real businesses and things that are incredibly not even pitchable.
Yeah, this is the RoboCop future.
Yeah.
The arms that come from the ceiling and safeguard you.
Well, like when people have arms that come from the ceiling, how do those arms move from one point of the ceiling to another? Is the assumption that just the entire ceiling is filled with arms? Is there a gantry system for the arms from the ceiling?
See previous episodes of Rail Network. It's prerequisite. Phase 1, Rail Network.
I hate it when
Phase
cartoons
2,
do
health.
this and like the robot arms always come from just right off screen.
Right off screen. Yeah, exactly.
Because the far more interesting technology is how to make infinite arms come out of finite space. All right, so we're going to grab bar patrons if they have trauma.
Which is mostly everyone at
Stamp
a bar.
them in some sort of way.
Yep.
And have doctors come sort them out. And we'll tell their loved ones that they have trauma.
It's just it's a big scarlet letter B that just gets painted on your chest if you're a bar patron.
However,
I'm sure they'll go over great.
However, like the mounted radars in job sites is interesting. Like there's a real business there probably.
Well, yeah, for the nice thing about radar is they're much more difficult to foul.
Yep.
As opposed to cameras.
Yep.
So, and they have much less privacy concerns, as you pointed out.
Yep.
Right. So having some understanding of here's how many people are on the job site.
Yep.
Here's what state they're in. Some of these radar are getting accurate.
And also, are there people in parts of the job site that are unsafe?
Exactly.
Yeah.
Some of these radar are getting accurate enough that I saw actually at CES. They're pitching it, I think, for human medicine, but maybe veterinary medicine, a remote stethoscope using radar.
That's cool.
Where it can measure your heartbeat and arrhythmia and everything from across the room.
You don't want to touch patients. They're a little icky.
There, yeah. Yeah, people go into medicine to not deal with humans.
That's what I always thought.
But yeah, so there's all sorts of secondary data you can get from accurate enough radar. And there's a fuzzy zone between radar and millimeter wave radar, which is getting into the security scanners you see at airports that can like pretty accurately
What's the
measure
effective range of one of those?
The security scanners at airports are pretty short. That's why they kind of sweep around you.
But like, let's assume that chips get smaller, electricity gets we get more efficient.
It's not even a chip smaller or efficient thing. It's a physics absorption in the air thing. As you go up in frequency, your absorption from just gas and moisture in the air.
Yeah, if you just like crammed more power through it, you could put out more waves.
So you're building a microwave at that point.
Yeah, that's fine.
You're just going to cook everybody who steps into the zone.
I won't have to worry about them having accidents on the job site because they're drunk.
Yeah, well, because they're going to be cooked turkey.
Yeah, and that, you win some, lose some.
I think the U.S. military developed a microwave radar weapon along these lines, right?
A number of attempts at radar weapons, microwave weapons.
Yeah, the problem with them is they're defeated by a sheet of tinfoil. So that, doesn't work very well.
Yeah, duh. That's real life, isn't it?
You just hold a sheet of tinfoil in front of you and you're fine.
if only our enemies had access. That's why we can't allow Walmart to enter into Afghanistan.
Because the tinfoil?
Yeah, you can't buy tinfoil. Can't survive the microwaves.
You heard it here first, folks. Literal tinfoil hat conspiracy.
All right, so I think our real business here is radars on job sites that are not bars, but we ended up starting a real business.
What's the robotics element? Okay. It's like an assembly line. People come on, and if they're screened and they're found lacking for whatever reason, just this big sweeper arm comes off and knocks them out of line. Like, nope, go back home.
Into a pit.
Yeah.
Into a Sarlacc pit.
Into the discard pile, just like the factory assembly line.
So I have a friend who's a company like this that is microwaves in offices to detect gunshots and automatically call 911, which he started when we were in NYC together in 2016 because he was a Brit in the U.S. for a month, and there was a school shooting that everyone thought was traumatic, and it changed his whole life. But I have no idea what school shooting it was because we're talking like 8 years ago. So that business is roughly, I think, $50 to $150 per detector. And then you have some number of detectors.
Why do they use radar?
Sorry, 50. No, it's microphones.
Oh, microphones.
$50 to $150 per month, per detector per month.
Yeah.
And a detector every 2,000 square feet of office or something.
Yeah.
Which is a lot of money for an internet-connected microphone. So I think for our radars in a factory, we could probably be charging in the range of $1,000 per radar per month. If they're high enough, you probably need a radar every like 3,000 square feet to get a sense of where people.
Their field of view is pretty limited. You can't really.
I'm thinking they're like 100 feet up. Is how tall I think the factory is.
Yeah. Okay. Fair enough. Yeah. So you need every few thousand square feet.
Yeah. So call it like 10, 20 grand a month, or 10, 20 grand a month, and you can decrease insurance premiums by X because you can ensure that no one's ever.
Once you have all this radar data, how do you process it into, like, is a person okay or not?
The cloud.
Machine learning magic.
AI.
We
have AI that knows when people are drunk, aka we're just copying the formula from a paper that was published 9 years ago.
So it's the radar waveforms are turned into text, and then the text is fed to ChatGPT.
And if we don't understand what ChatGPT is doing, we built another LLM that will decipher it.
To explain what ChatGPT.
Yeah.
Yep. Done.
Yeah, so that's a real business if someone out there wants to start something without real robots.
All right. Stefan claims 20% ownership.
20, I think 98.
Yeah.
The idea is all the real effort about a company.
That's how it works.
God, I hate that we started a real business. The robot arms kind of broke it. On to our real topic of today. Let's talk about SIM. Let's talk about radar some more. So, I think conversation about this has changed in the last. I think it's changed and it hasn't changed in the last 5 years. But a common kind of thought process for safety 5 odd years ago was like, you need to come up with a series of autonomous driving scenarios, ADSs. And these ADSs need to encapsulate everything that might ever happen on a public road so that you can run a series of tests.
That seems infeasible.
No comment.
Okay.
But like you need to capture every ADS ever and be able to show unit tests about how your autonomous vehicle will perform in every conceivable scenario they might ever.
That is utterly infeasible.
Well, I think you're just not thinking big enough.
So I've probably mentioned this example before, but there's a video you can find on YouTube of a test. Happens to be Tesla. I'm sure other ones do it too. Autopilot's vision on the dashboard of what it sees the world around it, and it's showing a road and the vehicle's driving and cars and whatever. And then it shows a stream of stoplights that appear and then fly towards the car. And you're just looking at the dashboard in this cell phone video. Like, what the heck? How could it possibly think there's stoplights flying towards it? And then the camera pans up and the car is following a truck carrying stoplights to be installed on the road. And like in my entire lifetime of driving, I've never once seen stoplights in transit.
To give you a response here that has been given to me in real life by qualified people. The thing you don't understand, Ilia, is that is an edge case. And to make autonomous vehicles safe, you need to find all the edge cases and be able to overcome them all.
That's not feasible. That is not reality. Like that is, it is, dear listener, it is my interpretation that there are more autonomous driving scenarios in existence than there are grains of sand, than there are molecules of water in the ocean. And that the idea of needing to capture them all is a Sisyphean task where you can do incredible amounts of effort and never truly accomplish it, and therefore forever have one more reason why you can't deploy. This is like a 1960s understanding of how robots would work, where in the 1960s, they were like, we're going to make full intelligent AI for the home. And how we're going to do it is we're going to program a giant logic tree of every single possible thing that could happen in the house. And like, it sounds ludicrous, but that is literally what they're suggesting here.
It sounds like a positronic brain to me.
Like the road is less controlled than the average house, right? You're never going to have a truck carrying stoplights drive through your house.
No, right? Not with that attitude.
Right? Like, that is such an infantile approach to the problem. It doesn't even make sense.
I wish I could read you a list of VC names who made this argument to me. A, I don't have it, but it would be shockingly large. And B, I would definitely never raise money from them if I did that such in such a forum.
I hopefully that's been going away recently, because hopefully one of the good things.
I actually think it's worse. It's probably worse now.
No, hang on.
Now you have no excuse to not have these scenarios. You have LLMs.
Well, that's what I'm saying. So I hope it's getting a little bit better now, because one of the good things LLMs is showing people is that you can feed it infinite amounts of data and you'll still get a bounded result set, which will still hallucinate and which will still do things incorrectly. And like, I think we're starting to realize as a society that like, there's no upper limit to how much data you can feed to 100% remove that problem. That problem will go from 99% to 99.9 to 99.999, but like it'll never be.
I do not believe the world is becoming as wise as you are assuming.
I have to hope so. And also, there's all this talk of like foundational models.
Yep.
And what we talked about this already. We griped about like, what the heck is a foundational model? But like, the idea is you should not be programming your robot to handle every single particular scenario. You should be trying to build a generalized system which can adapt between scenarios, which we totally agree with. Like, we have no problem with that concept. But like, that's specifically anti what this ADS is talking about, because that is not feasible.
I mean, I do not think people are getting as wise as you think they are. While it is now becoming popular to talk about the limitations of AI, and it's happening in conferences and the New York Times and all sorts of different papers, I do not think people still understand that set of limitations.
Yeah. And so I think coming back to our topic, right? Like, simulation, I think, will always, almost by definition, be bounded by what you can imagine you want to put in a simulation, right? You're not going to have, I say this and I'm going to build a simulation to have a stop sign on a truck. Great. But I didn't imagine the one where the alligator's crossing the road, or the one where there's an overturned cart of Cheetos. Yep. Who knows, right? And so simulation, I don't think, can get you to 100% certainty. That doesn't mean it's useless. Yep. I think simulation can get you to 90, 80% certainty relatively cheaply. And so definitely, like, we're not anti-simulation. You need it. It should be part of your verification process. It should be part of your integration tests. I think people underestimate the delta between a 90% crappy simulation, which gets you a good result, like what we use, and something that will get you perfect performance in the real world, which is something that, for example, Tesla puts money into for training their systems.
And I think that puts money into, I think a number that I've heard is like in the range of $400 to $800 million a year.
Yeah, enormous money.
Yeah.
Right, to the point where they're building their own chips and their own architectures, their own power delivery systems. Very cool, technical, deep data stuff. And even with that effort, I doubt they're getting to the point where even they're adding one more order of magnitude improvement.
Yeah.
right? Like it's such a huge bar to clear.
Well, then what's simulation useful for? Like, where does simulation actually work?
Yeah. So I think simulation has a really good place to get you to that first 90% accurate, cheaper than building a real robot.
Yeah.
That is a very sane goal. And that means
I think I'm also in the camp of thinking that simulation is really good at proving a use case.
Yeah.
Yeah. Like, hey,
it's relatively cheap.
If I gave you this UI and this was a real tractor and you clicked here and it did this, would that actually matter for you?
Yeah. Yeah. And like, you have to worry less about the realities of robots. Like physics isn't that much of a problem. You can reset
Remote start
quickly.
Not working.
Yeah, exactly. It doesn't run out of batteries, doesn't run out of fuel. Like your stuff doesn't get closed for no reason. So it is absolutely a very, I would call it essential tool. I think where it falls down though, without enormous effort. And again, this kind of comment of like, there are companies specializing in this thing, like Applied Intuition, for example, right? Where they specialize in very detailed simulations, but the effort they put in. I
don't think that's what they specialize in.
Well,
we can come back to that.
Let's get back to it. But I think as soon as you try to simulate things like cameras or LiDAR or radar or things that are very high data density and very specific to their use case, you'll get a 90%-ish accurate answer, but don't make the mistake of thinking it's 100% accurate and over-tune to this particular set of data. But that'll be said, about our comment about radar. One concrete example of radar is that people really think that radar is like LiDAR, but cheaper. And it's not quite. Because radar is very sensitive to angles of incidence of the energy, how big the target is, how reflective it is in EMI spectrum. And so in a simulation, generally speaking, unless you put an enormous amount of effort, you're going to get a very simplistic idea of like, whatever the object is, radar can spot it. Going beyond that to something like modeling reflectivity and multipath interference and angles of incidence is a very big step. And you'll still get a slightly better radar model, which will still not always correlate with reality.
Yeah, which is interesting. And I mean, I think like sensor simulation is one of those areas that people don't understand why it's as hard as it is. Because I mean, like, why can't you just take Unity and simulate out radar or LiDAR or any of those things?
Yeah, and you can. Like I was saying, you can do those things. It's effort. But you're not going to, don't mistake it for perfection. Don't mistake it for reality. You're going to get a okay result.
Yep.
And that's just because the real world is a lot more complex and messy than even the real sensors themselves understand, much less the simulation of the sensors.
Yep. Well, I mean, so going back to radar.
Yeah.
So radar's better at seeing metal. It's better at seeing thicker bodies or of chunks of metal, chunks of
larger reflected surfaces.
Larger reflective surfaces. I feel like radar has kind of become cool again in the last couple of years. I know in like the first DARPA Grand Challenge, some of the teams were like building their own radar from reading papers of radar design, and the Delphis and the Contis didn't sell to the mere mortals of R&D teams as of like 2004, 2006. As time went on, there became pretty plentiful radars. But LiDAR was the cool special sensor. At Starsky, we were weird because we were radar and vision and not at all LiDAR because, radar, automotive grade radar exists and doesn't shake itself apart at highway speeds, or didn't in 2017. But around that like 2017, 2018, 2019 era, there started being a bunch of companies who called themselves like HD radars. I know like we've looked at some of them, but the TLDR on them is basically a fighter jet radar can see where a fighter jet is 100 miles away, can see a relatively small obstacle very, very far away, very accurately. Right, and accurately enough to shoot a missile at it and get close enough that the missile's onboard stuff can figure out the rest of the way. So there started to be this effort of like, let's take these big radars that are maybe 2 feet by 2 feet and shrink them down to something that could fit on a car so that you could see every other vehicle on the road and maybe even see around corners and see through other cars in some situations. There's a company in Europe who's doing mining autonomy using just radar, just high accuracy radar. I think it's an interesting, like we're using radar for a number of customers where we're giving them a safety stack primarily powered by obstacle detection from radar. And I guess what's interesting to me about it is, A, this is an old sensor, so what's new or what changed to make it be hot now? And B, where does it still suck? Where is it still not good?
Yeah. I think to do a technical digression just for a minute, when people hear the word radar, if they haven't worked at these sensors, they're thinking of the old school moving green line on a circle on a battleship kind of thing. And that is fundamentally what radar still is. But what we've done since then, or what the industry has done, is that inside the little, for example, continental radar units, you'll have multiple antennas, multiple receivers. And they'll very carefully time the radar signal, because radar signal is omnidirectional, just like an antenna on a car or on a radio. By very carefully timing when the two active antennas are firing off, and then figuring out which one of the receivers are receiving it at one time, you can discriminate between signals coming in from your left or your right. And by having an array of these receiving antennas, you can now discriminate more accurately than just left or right. You can discriminate a few degrees by section and vertically as well. What's interesting about these radars is that because they've been tuned for the automotive space, generally speaking, they're very sensitive left and right. They're not very sensitive up and down. Their discrimination up and down is quite terrible, actually.
Yeah.
So they do have this directionality on how you mount them and which way they're facing. And what you're getting back generally is amplitude. So how loud of a reaction did you get from a particular direction? That loudness could be correlated with distance. There's a time estimate too. Or it could be correlated with size. Or it could be correlated with which angle is facing you, right? If you get a perfect retroreflector, it could be very small, but appear enormous because the amplitude returned is big. So a lot of the effort in modern kind of so-called HD radar, increase the amount of antennas, both transmitting and receiving, to get more discrimination direction, and increase the intelligence of your signal analysis so that basically this amplitude wave can be turned into a good confidence of a particular sized object in a particular direction and distance. And even better, because radar is affected by speed of the object, basically a Doppler effect, you can estimate the speed and relative vector of that object too. So it's a very nice single snapshot sensor, which gives you vector, size, and position, which is relatively unique. LiDAR, for example, can't get you, most LiDAR, let's call it, there are some, can't get you a great idea of vector. Camera data can get you maybe vector, can't get you a great idea of distance.
Unless you're using stereo cameras, you're doing some ML tricks.
Right, exactly. And so there has been a blossoming in radar, because the other thing with radar is it's not fouled by, or not as sensitive to dust and rain. Still is somewhat, but way less.
Why is it sensitive to dust?
Same problem, right? If you get enough density of metallicized dust, you basically look like an object, right? So you're going to get phantom objects pop in and out.
So it also depends on the type of dust. And
the type of dust and the density and all these radar sensors are dynamically tuning themselves up and down in power relative to what they're seeing. Because if they're really loud all the time, they're going to miss objects close in because they just get overpowered by the returning wave. So it might be that you're in a very empty environment with a little bit of dust, and that's the only thing there. And so your noise floor is now much higher. And so now you're seeing it more. Not common, to be clear. It's not nearly as sensitive to it as LiDAR or cameras are, but it still does exist. The main thing about using radar as a roboticist, though, is you want to see a LiDAR type image where every point in your cylindrical coordinate system has a return data. That's not how radar works. If you point a radar, unlike a LiDAR, if you point a LiDAR at a street scene in some suburb, you'll see points returned from the cars, from the ground, from the trees,
any
from
of
the
these
whatever.
very, very pretty images that we've all seen.
Right. If you point a radar at the same scene, you're going to get 1 or 2 points per car, and that's about it. You might see the trees if they're close
Which is
enough.
why they're often visualized as just like a big box.
Box, right? You might see the trees, you might not. You're going to get very few points on the ground because most of the energy hitting the ground is bouncing off and away. And you're not going to get anything on the grass, on the trees, on the whatever. So you can't use radar to map out your scene very well. Again, now that's changing with HD radar because the more antennas, more intelligence and processing, you can lower your noise floor so you can listen to these.
And there's been a number of companies who are working to basically with magic software turn any regular radar into an HD radar.
Exactly. But there are limits to what you can do. The main thing that radar suffers from that LiDAR isn't as sensitive to is this idea of multipath. So if you have 2 objects close to each other, the radar signal is going to bounce between them and come back and give you an erroneous signal of the summation of the distance between the 2 objects rather than the distance to the 2 objects. So it's kind of a weird effect. But so radar is making a comeback.
Is this kind of part of why it's so hard to simulate radar?
Exactly. Right? Not only do you have to consider the size of the object, you have to consider this multipath effect, you have to consider
simulating
reflective the
it
object
isn't
is.
just a bunch of straight lines to returns.
No.
It's a bunch of like weird wave stuff that probably also gets heavily impacted by other environmental things.
Exactly. It's almost closer to ray tracing, which has started to come back up in computer vision recently, but it's almost wave tracing rather than ray tracing.
Yeah.
So it's fairly complicated. There are companies, again, who specialize in doing this,
Yeah.
but it's very expensive and computationally expensive to do.
So then where's radar really good?
Yeah. So I think radar, because it has no moving parts and has no lenses, it could be much more easily weather sealed. It's much more robust to vibration and heat and noise and dust and things we talked about. And it's relatively cheap.
Yeah.
It's cheaper than any LiDAR. It's cheaper than any camera. There are, of course, expensive models of everything.
Yeah. And there's 2-dimensional LiDARs that cost $100.
$30. Yeah, exactly. But apples to apples for similar performance and quality and robustness characteristics, radar is going to be a quarter or a tenth of the price.
Yeah.
So you can have a lot more of them, which means on larger vehicles, you can position them more carefully. You don't have to have this. One problem with LiDAR currently is LiDAR is so expensive that your 3-dimensional LiDAR is, you only maybe get one of them or two of them, right? You'll see these autonomous vehicles, test vehicles that are peppered with LiDAR, like Cruise, for example, right? Which is great, which is wonderful for them.
It's a great sensor.
But it is not feasible at scale today.
Yep.
Because each of those is $3,000 to $15,000.
And many of them break pretty easily.
Right.
Yeah.
And so
it's a very expensive, highly sensitive wear part.
Right. And so you can't, as an average consumer on a car, you can't afford to spend $80,000 or $150,000 on LiDAR.
Yeah.
So, but you can afford to spend maybe $1,000 on 4 or 5 radar pucks and position them around. Coming out of the automotive space, even in robot design, even indoor robots or industrial robots, if you have one LiDAR on your machine, you kind of have to position it centrally somewhere. Yeah. And so that dictates the geometry that your machine can take. So that limits your industrial design.
In many ways, like internal combustion engines are designed around the engine, or internal combustion vehicles are designed around the engine.
Yeah.
Many robots are designed around their LiDAR.
Yeah, or their sensor profile.
Yeah.
Exactly.
Yeah.
Yeah. So that radar gives you a little bit more flexibility there. The other nice industrial design component is that radar can be completely hidden behind transparent materials like plastic.
Yeah.
So you can just not even
know
need
to look at them.
Yeah. Yeah, you don't even need to know that the sensor
which makes
exists.
the product designers happier.
Yeah. And the customer at the end of the day.
Yeah, right? Frankly.
It's so you have this kind of magic piece of technology that can see where it is with no visible sensors. That's kind of cool.
So radar is good for some things, bad for other things. Simulation, good for some things, bad for other things.
Yeah. Groundbreaking hot take, I know. Sorry, this is engineering. That's
the
how
answer
it
in
goes.
robotics, it depends.
It depends. Yeah. Super divisive.
So
answer.
going back to what I think Applied Intuition actually does, I think Applied Intuition definitely has some sim stuff. They've bought stuff like the makers of CarMaker, I believe they now own. So they have some like visual looking sim stuff. I'm sure they have some things that look like a very dressed up version of Gazebo. I think the primary product is CI/CD infrastructure for large robotics teams within large companies to be able to make consistent progress and test their progress and show their progress over time, with occasional outputs that look a little bit like a Gazebo video, so they can show the idiots on the business side of the house, hey, look at our autonomous system that worked here.
Yeah. And actually,
that is why they're currently worth $9 billion, because they're really good at selling very expensive software that one buyer thinks does X and the user thinks does Y.
So actually, that's a very good point. Building simulation, like full on, real simulation as part of your CI/CD is legitimately difficult. It seems like one of those like, just have a little GitLab runner and stick it in there, and there you go.
Oh, we made some changes. Do we still stop when someone slams on brakes in front of us?
It sounds beautiful, but getting into the details, what's really interesting is that you really have to change your mindset on how you're testing software in simulation. Because if your simulation is at all realistic, even approaching realistic, you're going to have some variance in your physics model. You're going to have some variance in your sensor model. You're going to have some noise profiles. Right? Again, realism is that your sensor will have noise. Yeah. Which means if you write your test as, I expect to get exactly this sensor profile, your test is going to fail a lot. And if you've built a CI/CD system, what you really want to minimize is false positives and false negatives.
Yep.
And a lot of false negatives have failed tests because your test is too precise for a realistic sensor. we'll either get your test turned off, which means you have no CI/CD system,
Yep.
or we'll get it worked around.
Yep.
And so you have to be really careful about how you're building your testing with simulation in mind. You can't think of it as a deterministic, like a lot of software engineers, when they look at testing a UI or a backend or something, it's like, I press this button and 50 milliseconds later, this thing happens. Great. That's a great test for that. Robotics simulation testing is much more involved, and you have to be a lot more clever about how you build your test cases.
And what success looks like versus what a failed test looks
exactly,
like.
Exactly. Because you're going to be, or else you're going to be fighting endless false positives, false negatives.
Yep.
And another concrete example, you want to make sure that your robot, your whole stack, plans from A to B in some complex simulated environment. Even if you keep the complex simulated environment exactly the same every time, as your software develops and your planner changes, suddenly you're going to take another route because it thinks it's more efficient or because the planner is a little bit better. And so if you built your test to be like, robot shall complete testing in 5 seconds, and now it's taking 3 seconds because it's better, suddenly you're failing your test. These are simple, trivial examples.
Yeah.
But it's again, like that ADS. It's a whole stack of these trivial examples that you need to be clever.
Well, why? Sorry, let's dig on that a little bit more. Why would there be non-determinism in my tests in a simulated environment? Like, can't I say when physics works like X and when sensors work like Y, this should work?
Well, so concrete example, if you want to be realistic, and this is what I keep saying, right? If you want to be realistic about your LiDAR simulation, you're going to have some noise in your LiDAR return.
Yeah, sometimes it doesn't see stuff. Sometimes it gives you 84 points on a particular object. Other times it gives you 30.
Right. Even again, a concrete example, my robot needs to go through a doorway, like we were working on Astro at Amazon. The doorway that the LiDAR depth sensor is seeing is 24 inches wide. So my path planner picks a plan that just skirts the edge of this doorway. On my next simulation run, because of noise, it's now measured as 23 inches wide. So it's going to take a slightly different path that might nick the edge of the door, which arguably is a failure of the planner, but also arguably is just a result of the noise.
Yeah.
And so you need a plan around these kind of, it's that compounded times 100, because every feature you're seeing is like that. Your physics simulation of the grip of your vehicle on the ground is going to, again, if you want it to be realistic, it's going to have some noise component. It's going to have some variability between different surfaces. So it just stacks up pretty rapidly.
Whereas if you're testing, can I reliably call AWS every 200 milliseconds?
Yeah, that's
that really should just work.
Right. Right. And again, like I'm not trying to make this out to be an impossible to solve problem.
Yeah.
I'm saying you just have to be cognizant of the fact that you're testing a simulated real system, which means there's variability, which means your tests cannot be black and white deterministic.
The answers to tests are more like distributions than they are like
exactly. They have to be distribution.
Binary.
So when you ask the question,
which is not dissimilar from the challenges in testing AI systems.
Right.
Yeah.
Exactly. They're very related. When you're building a metric you want to test against, it's not, aside from trivial cases, it is not feasible to say my path planner will succeed 100% of the time. If you set that as a goal, you're going to fail.
Yeah.
What you should say is greater than 95% of the time, my planner will succeed under 5 seconds. That's a good metric.
Yeah.
Because it has multiple things built into it about the fact that it's planning somewhere around less than 5 seconds.
Yep.
And that it is succeeding some percentage of the time, which is a distribution.
Yep.
That's the sort of metric you have to think about.
Which goes back into topics that I believe we've discussed on the podcast before, of metrics themselves being such a cluster.
And so important.
Yeah.
So important and difficult to get right for robotics.
I have a friend coming by the office tomorrow who has had some trouble in SaaS and wants to start a robotics company. And I was like, oh, you're going from hard to way harder.
Way harder.
And what do you mean? And when even the metrics, let alone the testing, let alone the thing itself, are all variable and hard, it's a unique sort of problem that you only get to have in the wonderful land of robots.
Exactly.
And with that, what are we going to talk about next week?
Well, first of all, apologies for missing a week or two here. Did Ed Nierbuyer's episode of Talking to Stefan come out yet?
Yeah.
Has? Okay, go listen to that in the meantime.
Yep.
If we ever miss another episode, which will never happen again.
Yep.
Stefan guarantees it.
Yep, guaranteed. Guaranteed with Ilia's blood.
Ah, damn it.
Yeah.
I was going to
Merchant of Venice style.
You got to it first.
Yeah.
You can have your pound of blood, but no flesh. Huh?
Shoot. How many pounds of blood are in the body?
Probably more than a pound.
Yeah, likely.
Isn't it like 4 gallons?
I
or
just started
something
watching
like
Breaking Bad, and there's some talk about the chemical components that go into the body, and like, oh, it adds up to 99%. You know, where's the remainder? Like, just rounding error. But yeah, so next week we'll be talking about Breaking Bad. We'll just go into a full detail. And if you never hear that episode, it's not because we didn't record it. It's just because, we didn't share it with you particularly. But we'll find something to talk about, and we'll probably do one next week too, I bet.
that. Alrighty.
All right. Well, thank you all so much for joining us.
See you next time.